Are you able to see the screen? The presentation slide?
Yes, sir.
Okay. So last time we have seen a simple VHDL implementation of a sequence detector. All right. And we have already gone through the traditional approach, the conventional approach, as well as the VHDL implementation. Now you'll see that VHDL implementation becomes very, very easy, provided you understand the various different parts of that particular design. So just to have a brief overview, refreshing of this particular design, the implementation, we started with the library declaration, the entity declaration as usual. And then in the architecture, you see that we have defined the states. Okay, so this is a user defined data type called as state type. And naturally, we had only 4 states, A, B, C, and D. Okay, and then what we did was we used signals with names as present state and next state belonging to that particular data type, state type. The basic design will compose of 3 different processes. So every state machine can be designed with either there are 2 ways in which you to do it. One is called as a 3 process style. The other one is called as a 2 process style, which we will see later on. So this particular example uses the 3 process design style. The very first process, I'm going to label this process as state underscore machine, and the sensitivity list is the present state. So whenever present state changes, this particular process is going to be executed, so as to say. Okay, now let us go inside and see. So when the present state is A, what should happen? Naturally, this is a conditional thing, because this basically decides or tells you, if you look at the state diagram, you'll see that whenever there is an input, whenever the present state is A, and whenever there is some input, there will be some output, and the state may change. Okay, specifically if is input to whenever the state machine is in state A, and if the input X is 1, in that case Y is 0, but it advances to the next state by shown by this particular arrow. So this exactly is what we are doing here. So if X is equal to 1, the next state is assigned B, because the next state is going to be B. Otherwise, the state remains the same. Okay, it falls on the same state, falls back on the same state. When this present state is B, similarly, when there is a x is equal to 1, but remember that x is equal to 1 is not what is expected, because our sequence that we are trying to detect here is 1 0 1 0. So whenever the next bit is 0, it should fall back to the original state, saying that sequence, the part of the sequence also has not been detected. So if it is 1, so this particular arrow, okay, this is shown by this part of the code. So if x is 1, next state is A, so it goes back to state A. Otherwise, if it is 0, else next state is assigned C. So it advances to the next state. Similar is the case with C and D also. Okay. So this is basically only the assignment of the next state depending on the input. So this part of the code decides that. Second is the clocking. So you have a clocking process. Naturally, when we say it is clocking, this process is triggered whenever the clock changes. And naturally, we are detecting the rising edge of the clock. So clock tick event and clock equal to 1. Then naturally, what you have to do is you have to assign the present state, next state value to the present state value. So the present state becomes whatever the state value that we had calculated or computed in the previous process will be assigned to that. So state change will occur only on the rising edge of the clock. Okay. Similar is the case with, here in this case, I'm going to also assign at the same time the output. Whatever is the value of temp is assigned over there. Okay. You can see here temp is in out, so I can read in and write to that also. All right. In that case, the third process is called as a melee output, and the process is triggered whenever there is an input and the present state. Remember, if you require only a Moore output, you don't require this process. Okay. So Moore output can be whenever you require a Moore output, you don't have Moore machine. You don't have to use the this third process over there. Okay, what does it do? If present state is D and X is equal to 0, then so whenever it detects the new input which is a part of the sequence, this temp will be assigned 1. Okay, and obviously remember that all these processes are concurrent. Even though whatever is there inside the process happens sequentially, the process on its own is a concurrent one. So all these things are happening simultaneously. So don't say that, okay, this is later on it has assigned the value of temp. So what will happen to the value of y, because we are assigning the value of temp to y? No. Whenever we are looking at such a kind of code, it is assumed that it is understood that it is a concurrent process. It is a concurrent, let us say, action. Okay, so this is actually a 3-process style of the state machine. We have already seen this timing diagram also and seen that whenever there was an incorrect sequence, it fell back, the present state fell back to 0. The states were encoded as 0, 1, 2, and 3, and that is what has happened. All right. Whereas in case of the correct sequence, it does generate the output. So it has detected. You can see the correct sequence, and it has detected the sequence. So the output is asserted over there. This was the synthesis result, no need of going for that. And then we started to have some kind of a template for the procedure for Mealy state machine. So this we are going to call this as procedure number 1. As I said, there are 2 different ways in which you can do, I mean, similar but somewhat different ways in which you can design the state machine. So you have the very first thing that you have to construct the entity with input, output, reset, clock, in-out. These are basically, this in-out is required for temporary storage. Okay, so these are the basic necessities of any state machine. Okay, as far as possible, use the bit type. There are some reasons for that, because we don't have to really, in that case, bother about the other types of signals coming into it. Specifically the multi-valued logic signals. Then declare the states. So we are using the user defined data type and declaring the states. Declare the signals, present state and next state, and all declarations will be between architecture and beacon. This is understood. And simulate only after synthesis. Now this is very important, because maybe it is not possible for us to get the direct output if we do it before the synthesis. Okay, there are reasons for that, because we are not explicitly allotting the encoding. The VHDL compiler is not able to directly assign the encoding of the states, and so it may lead to a problem. In fact, even if I tried that, I don't have a synthesis tool with me. But even if I tried with without simulation, synthesizing without simulation, or rather simulating without synthesis, in that case, my state was not changing at all. So I said simulate only after synthesis. This is very, very important. So this is the template. So library declarations, state machine, port declaration, architecture. Now here between architecture and begin, you have to declare the state type, and of course the signal that you're going to use, that is the present state and the next state. All right. So this is the first part, that is the state machine. Again, the same thing, whatever we have said over in the earlier slides. If some input condition is checked over here, and then the next state is assigned some certain value, which is B in this case, or else if that condition is not met, it is B. It is A again. It fallbacks to the same state. Okay, and so on and so forth. So that is basically what is required over here. Now, if you are declaring it as a std underscore logic type, then when others clause has to be there. Okay, otherwise there will be an indeterminate output. Then the clocking process and the Mealy output process. So this style is called as the 3-process coding. So it is possible that you may be asked in the examination that you have to write, you have to design a state machine using either 3-process coding or 2-process coding. Okay, and then finally we will see the vending machine problem. But before that, I would like to tell you how this problem of simulation before synthesis happens. So just hold on for some time before I switch over to active HDL. So is the active HDL screen visible to all? Guys?
Yes, sir. Yes, sir.
Yes, sir.
Okay. So here you can see I've written the exact same code. All right. See that? Library declaration. Okay. Instead of std logic, we'll try to use bit type. And then you can see it is exactly the same. I've written this code for that sequence detector. So let us compile this. Okay, it has properly compiled. Now initialize the simulation. Put all this, add this to the waveform, and then already I think clock has been assigned a clock signal of 1 megahertz. That's fine. So let us try to simulate this. Okay. See the difference over there. One more thing. If you want to simulate before, a synthesis, you have to use the bit type. Okay. See the next state has been assigned B now. Okay. So the clock edge, you can see. Can you see this here?
Yes, sir.
So this is the one. Okay, shall we start with? Shall we reset the simulation and start with 0 so that the next state also happens to be? I mean, we'll be having a simple demo of this. Okay. Let me initialize the simulation once again. Select all. Add to waveform. Okay. X has been given a value of 1, which let us revert it back to 0. Okay. And then I'll run this. So there is no change. Of course, we are yet to see the clock coming here. So even if the clock signal arrives, you can see here very clearly that guys, am I audible?
Yes, sir.
I think there was a call drop. So my question is, what is the sequence that we want to detect? Tell me.
1010.
1010. Okay. So I'm having a 0 right now. So naturally the next state is not getting changed. This is the first part that you can see here. All right. Now I'm changing this X to a different value. So this is the first bit. Okay. So in that case, it should have changed. This is basically a problem before synthesis, I guess. So we have to reinitialize the simulation in that case. Okay. It won't change like that. So that is the reason why I said we have to simulate after synthesis only. So you can see here. Okay, let us see what happens. initialize the simulation once again. Now add all the signals to waveform. Select all. Okay. Now see what has happened. Do you see the change? Do you see the change? Guys?
Yes, sir.
So what has happened? Whenever there was a rising edge of the clock, the present
Present.
state is assigned next state. I mean, whatever we calculated as the next state, that was assigned to that. Okay. Let us see if we can. It won't change actually because, as I said, let us try. That's what I'm saying. Yes. So it has now changed back to A, which is wrong. So I mean, this is basically the problem. Okay, next state again. I'm forcing it to 1. And it remains stuck over there like that. So I can't do that in any ways before synthesis. That's the problem. But believe me, after synthesis, I have tried with earlier whenever I compiled it. I don't have a synthesizer right now with me, but you can try with whenever you must be using Xilinx. So with that, you can definitely try. Okay, is that fine?
Yes, sir.
It should be possible for us to put a pattern of some sort. Okay, let us see if can do that. No, if it is random, it won't work. Value counter. Let me see if I can use a drive strength and then cannot force it formula 1. Okay. Let me see if I can use this value 0, time offset 0 nanoseconds, value 1 after 10 nanoseconds, 0 after 20 nanoseconds. Um, okay, I can do this also. 0, okay, 1, this after 30 nanoseconds, again 0, yes, 40 nanoseconds. Let us see if this works. No, it doesn't. The signal was there, but see, it failed to change the output. Again, the problem is because we are not synthesizing it first of all. That may be the possible reason. Okay. Anyways, you have to try this on your own. All right. Let me see if something I can change here. To initialize simulation, select all, simulate, add to waveform. We had a formula. Let me see if I can use a drive. Okay, it cannot force signal. Why can't it do that? Okay, anyways, let us not waste our time here because I already had that issue earlier. And that is the reason why I said that we are going to have simulation only after synthesis. I'll switch back to the presentation. Is the presentation slide visible to all of you? Guys?
Yes, sir.
Okay, have you started with writing the design using Xilinx? Tell me. Guys? Guys, please respond.
ट्राय केलंय मी
बरं.
So I'm
पण
using active
सिंथेसिस
HDL.
नंतर सिम्युलेशन मध्ये एरर येते.
सिम्युलेशन मध्ये एरर येत आहे.
हा.
Active HDL I have started using. It is working fine.
Yeah, active HDL we don't have any problem. It's basically what I'm why I didn't use Xilinx is because Xilinx is too big. Okay, it unnecessarily will consume the hard disk space. It's about 10-15 GB, and I can't afford to do that at this point of time because of the limited space. So the best alternative which I found was active HDL, which is very good in fact. Okay, it's more, the idea is much more advanced than Xilinx. That is what I presume. But just for practice, it is good. Ultimately, you have to use the synthesis and all that. So you have to finally whatever code you write, whatever design you write in active HDL, simulate up to functional simulation, and then copy the same code or the same VHDL file to Xilinx and start using it. Right. So that is the way in which I used to do. That I used to write everything, all the VHDL, everything in active HDL, and then once I was satisfied with the functional simulation, I used to switch over to Xilinx for the pin allocation and all those kinds of things. All right. So this is basically what we are trying to do now is we'll be taking up a slightly complex example, the example of a vending machine. Okay. So first of all, the specification of the vending machine will start with a word description. Okay, so a state machine is to be designed for a cold drink vending machine. Machine will accept the coins of these denominations, rupee 1, 2, 5. Okay, one coin at a time. And let us assume that we are living in a very enlightened and golden age, so that cold drink is available for 5 rupees. Forget about the inflation and all that for the time being. Okay, so after 5 rupees, total of 5 rupees is reached, you will be getting the machine will release the cold drink bottle. Okay, so there are various ways in which the user can input. So you can first use 1 rupee coin, keep on depositing 1 rupee each 5 times, and then the total will be obtained like that. Okay, so this is basically a very classical example of state machine. So this is basically the state diagram. Try to understand this state diagram. I give you 5 to 10 minutes. Try to understand this and see if it is you are able to logically understand this state diagram. Remember, first of all, you have to start encoding the type of input. So what I have done here is rupee 5, 2 and 1. I have encoded as 3-bit sequence or 3-bit, let us say, word pattern. And then MSB corresponds to rupee 5. The intermediate bit corresponds to rupee 2 and the LSB corresponds to rupee 1. So whenever somebody is inputting, let us say 1 rupee, this RE, this bit will be high, and so on and so forth. Okay, and the output, of course, is to be a single bit. So start and end, I call this as a term, that is termination of the sequence. Okay, so let us see logically. Hello.
Yeah.
Hello.
Yeah, there was a call drop again, I guess. Okay, so I start whenever the user inputs 1 rupee coin, in the scene here, it advances to the next state A1. Another 1 rupee advances to A2, A3, A4, and ultimately the last one. Okay. When it comes to this particular state, it will also output a 1, indicating that the sequence is complete and the machine can release the cold drink bottle. Okay, let us take the other extreme, that the user is inputting 5 rupees coin directly. So it goes directly to the termination, and over there you can see 100/1 simply means that when the input is 5 rupees, you have to generate the output, so that's to indicate the release of the vending machine, release of the cold drink bottle. Are you able to understand this?
Yes,
Guys,
sir.
now try to decipher these intermediate states. I give you 5 minutes for that. Okay, instead of that, let us have an exercise. You have already seen the state diagram. So take out your notebook and try to draw your own state diagram for this vending machine problem. And then you can compare it with whatever I have done. Okay? Guys,
Yes, sir.
please do that. It's going to be an exercise for you. And tell me when you are finished. Yes, have you finished? Guys,
Yes, sir.
all of you?
Yes, sir.
Okay, then compare it with whatever I have done.
Sir,
Yes.
sir, I have
Go on. Go on.
B1 when it goes
Sorry.
after B1 when it goes to A3, then there are two coins of 1 rupees. So it will not complete total 5 rupees.
Which one?
After start it goes to B1, then
Goes to
A3.
B1. B1 is 2
B1
rupees.
is 2 rupees. After that A3 it will be, after A3 it's only 2
So 2
rupees.
plus 1, 3. 3 plus 1, 4. 4 plus 1, 5.
Sir, it can
Oh,
also
okay.
go like after B1, it can go to A2.
Sorry?
After B1, it can go to
Yeah, it can
A2.
also. I'm saying that it is quite possible that you may have different solutions. All right.
Okay. So do we need to consider all the possible?
Yes, you have to consider all the possibilities over there. Okay. So you said that you are saying that after B1, it may go to A2.
Followed by A3 and A4.
Why will it go to A2? Why should it go to A2? In what condition will it go to A2? It will never go to A2 from B1. See, you already have input 2 rupees. Okay. Then if you input 2 more rupees, it will go to B2. It will never go to A2. Try to understand. Hello? Guys, are you there with me?
Yes, sir.
Yes, sir.
So do you
Yes, sir.
understand that from B1 it cannot go to A2?
Yes, sir.
One interesting thing that would be maybe that you have it in mind maybe was that A2, the accumulation of the amount is 2 rupees. B1 is also 2 rupees. So are they equivalent? That may be the question in your mind. Hai na?
Yes, sir.
Yes.
No, actually, I was thinking like if the user first inserted 2 rupee coin, then
Yes.
if he inserted 1 rupee coin in that case.
Sorry, start again.
If the user inserted a 2 rupee coin
2 rupee
first.
coin. Okay, 2 rupee coin. So it can go directly to A2 also from here.
Okay.
That would have been possible. So this is just to make sure that you have different paths. I was just making sure that it was a simple path. Later on, we can optimize this. Maybe A2 and B1 are both equivalent states. And during state reduction, you can eliminate one of them. Are you getting this?
Yes. Okay, sir.
So maybe if I have a path like this 0 1 0 / 0, it can go directly to A2. Yes, that is a possible solution. Got it?
Yes, sir.
Yes.
But from B1 it cannot go to A2. Okay. So have you understood the concept of the state diagram here, specifically for vending machine? So once you are in a position to draw a state diagram for a vending machine, it is easier for us to write down the code for that also. Okay. So here it is. So again starts with library declaration, entity declaration. What are the various ports? Clock, reset, which are bit type in bit. Then you have input as bit vector. Remember, we have the input as 3-bit format and release as the out bit. Okay. Then you have the architecture. Again, state types. The types of states. The declaration is start A1, A2, A3, A4, AB1, B1, B2, and terminal state. Okay. Signals: present state, next state, and state type. Signal, temp, bit type. This is the process for present state and input. Now you'll see that this is a little bit different from the previous coding style. Okay, so this changes whenever there is a change in the present state or input, both. Okay, so when start if input is 0001, next state, so on and so forth. Temp is your output. Okay, this is for A1, A2, A3, AB1, B1, all the states are covered over here. Okay, now this is the clocking process, clock and reset. Okay, so if reset is 1, then it goes back to the start state. Otherwise, if there is a clock tick event and clock equal to 1, rising edge of the clock, then state assignment will be here. And that is the end of it. So how many processes do you see here? Guys, how many processes do you see? How many processes were there?
2 processes.
Yes. So this is a case of a 2-process coding style. Remember that. All right. Okay. This is what we get as a result. Okay, I'll show that in live action. Now this was already synthesized, and then I have the synthesis output also with me earlier. So in that case, it may work directly. So let me just shift over to active HDL again. So do you see the active HDL screen now?
Yes, sir.
All right. So this is what we had talked about. Let me initialize the simulation. All right. I've already have the clock. Yes, the clock is already there. We'll start with a simple case of the input. Now this is the MSB. So if I run this, you can see what has happened. It simply means that what? What is the user input? What was the user input? What was the user input? Guys, what was the user input here?
5 rupees.
Yes, the user has input 5 rupees. Okay, let me start this again. It's getting a little bit cluttered here. So I'll start the simulation again. All right. Now the input is 5 rupees and see what has happened. Something has gone wrong, it seems. Yes, I think should increase this to different value. Anyways, what you see is that the release signal has been triggered. See, so that it has triggered the release signal, and the bottle will be released. Okay, so let us go to the reset. and add. Okay, then run it. So you see that the present state is now start. Okay, input also I have to change. So input should be 0. All the input was 0. You see, since the input was 0, now this is the starting point again. We'll try with different combinations. Okay, so this was 5 rupees. INP 0 was 5 rupees, 1 was 2 rupees, and this was 1 rupee. Let us start with this one as 1 rupee. Reset, I'm going to make 0. Let us see what happens. Not forced properly. Okay, this is it. So I'm getting the first change. See that? Do you see that? A1. Since A itself was, I mean, the 1 rupee coin was again inserted, it became A2. If I go on advancing this, it will go to A3 and A4, and finally it will terminate with the release of the signal of the Coke bottle. Okay? So you see that it will be released now. It is not yet released. So yes, this is where it will release after the completion of that sequence. Are you able to see this?
Yes, sir.
Yes, sir.
Okay. We can try other things also, but I mean it is going to be a moot question if we go on trying some other things also. But have you understood the concept of how to write the VHDL design for the state machine and then simulate it and see the result? Okay? Have you understood, all of you?
Yes, sir.
Yes, sir.
There is an assignment given to you. I hope you already have started working on the assignments. Okay? All right?
Yes, sir.
Okay. So as I said, I got the results. Let me shift over to PowerPoint presentation again. Okay, so this is what we have seen. This is what was observed over there for 3 different cases. Okay, so this gives us with the procedure number 2. That is a 2 process style. Construct entity with input output reset clock. Declare states, declare signal, present state, next state, declare signal, temp, same size as the output. Okay, this is the template, library declaration, the state type declaration basically. Then you have the present state, next state belonging to those type, and signal over here like this. This is the first process. Remember in this particular style you have 2 sensitivity list parameters, present state and input. Okay. So there is an additional statement here. Earlier it was not there. See that? That is how you can combine convert a 3 process machine into a 2 process machine. 3 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 process machine. And then you have this. This is the simplest way in which you can do it. So this style is called as two-process coding. Please remember these two styles very carefully. Okay. Then there are various types of outputs also. If the output is stored, so we do not use the temp signal for output assignment, directly output the assignment. Okay. So if the temp may not be required at all, if you don't want to store it. If you want to store it, in that case, obviously, it will be stored with an additional flip-flop over there. Okay. So in that case, use the temp signal for output assignment. Then we come to what is called as the Moore machine design. Now this machine generates output based only on its current state. We already know that. Hence the Moore machine output is usually synchronized with the system clock. And we know that once it is synchronized to the system clock, the chances of metastability are very, very less. In fact, none at all. If it is a Moore machine. So Moore machine is characterized by more higher reliability as far as the metastability is concerned. In this particular process, the machine is to be designed in a similar way as to the design template number 2. Okay. So we'll start with a simple example, BCD counter. Now here you have the state diagram for the BCD counter. As you can see, there are 10 states, 0 to 9. Okay, and whatever is the output of the state, the coded state, that is the output of the machine itself. So there is no input. The only thing happening is the clock and of course the reset. So whenever you have a reset, you go back to this particular state, whereas when you have an advancement in the clock, you advance to the next state and then come back to 0. Is this fine? Why is it called as a BCD counter? What is a BCD, binary coded decimal? Guys?
Yes, sir.
Why is it called as BCD?
Digits after 9 are
Yes, there are only
9 digits.
9 digits.
I mean, digits after 9, we assign them alphabets.
So you are having 0 to 9 as the digits, but there are 10 digits, isn't it? 0 to 9. Count them. So it's a decimal counter, basically. Goes from 0 to 9 and back to 0. Alright. This is the code for the counter. Library declaration entity. It is going to follow the similar kind of procedure as design procedure number 2, that is the 2 style coding process for the mealy machine. Clock reset, there is no input. Output is directly a 4-bit vector. Alright. Then you start with the architecture, the similar state declarations, 0 to 9 states are declared, present state, next state, that's all. There is no temp, nothing. This is the process. Whenever the present state changes, next state will be assigned. That's all in this particular thing. A very simple thing. If the present state is 0, naturally we want it to advance to the next state. So next state is going to be assigned 1. If it is 1, assign 2, and so on and so forth. Finally, if the present state is 9, it should be assigned 0 back again. It is going back to 0. Okay? Yes. Is it all? Or something is missing? Is that all, or is something missing? Guys? Guys, tell me.
Quotation also.
Is something missing there?
In code, sir.
I mean, is this the complete? Is this the complete? Yes. Is anything missing? Just a moment. All right. Yes. What was missing? The clocking process itself is missing. No. There it is. So the clock and the reset. So it has to take care of the reset. When it is reset, it has to go to the state number 0 or the state labeled as 0. Otherwise, clock tick event proceed on to the next state. This is a simulation output. Let me see if I can directly get this simulation. Okay, what I'm going to do is we'll create a new file and see what happens. Okay. Add a new file. Okay. Here what I'll do is I'll create a clock. And reset output Q, which is going to be a 4-bit output. That's all. It should be similar to whatever we have written here. Okay. So here I will declare state machine. The clocking. Compile it. Okay, something was wrong here because reset RST. Okay, it was RST, not reset.
It is Q, sir, not D.
Yeah, not it should be D, right? Okay.
Yes.
Still, I'm having a problem here. It should be RST. Okay, so we have compilation here directly. Initialize the simulation. Let us see what happens. Clock. Reset should be 0. Okay. Are you able to see this? What is happening, guys?
Yes, sir.
Okay. So what output I'm going to get is it is going to go ahead. It's going to be working as a counter, and from 0 to, let me compress it a little bit, 1. So 0, 1, 2, 3. After 9, again it falls back to 0. Okay? So this is exactly what we have expected. Okay? This is much more easier design, the Moore machine, specifically used for counters and all such things. Okay? Is it fine?
Yes, sir.
Yes, sir.
Okay, let us go back to the PowerPoint. Okay. So, state machine design, we have already seen that it can be very nicely, very elegantly designed using VHDL. Now, this active HDL actually supports, in fact, I think Xilinx also supports that design entry via various different methods, and specifically for state machine, you can directly generate the VHDL code after entering the state diagram. Okay, this is what I had done earlier. Okay, so let me see if I can reproduce this again. This was done long time back, so if I don't know whether it will be possible, let me try. Okay, let me switch over to active HDL once again. So I have created a new design, BCD underscore auto, because automatically it's going to create the VHDL for us, state diagram. So VHDL, sorry, this should not be the case. It should be new state diagram. Let us see what happens. Okay, start. So again, clock, reset. Output was D. Let us remember that. Okay. So I'll be having such a kind of screen. I can start drawing the states. Okay, let me just reduce the size. Okay, so let us see what happens. This has to be D is assigned. There has to be a clock also. So let me see. Okay, so we have successfully compiled this. You can oh, sorry. I didn't give any stimulator to the clock, so it was not forming. Okay, so here it is. You can see the counter advancing into the next state. See that, guys? Do you see
Yes,
that? So it was a simple thing to do that, and it took only few minutes instead of writing the code. But of course, this is not expected. You are not expected to use this directly. But once you go onto the field in the industry, you can use such nice wizards and methods for. So this is another method for generating the state machine. Simply draw your state diagram in the editor. Okay? All right. Is it all right, guys?
yes, sir.
Okay. Let us, for just for fun, let us see what is the code that is generated automatically. You can see here. So this is the automatic VHDL code being generated over here. Okay. Fine. Is that fine? Okay. Let me switch back to the PowerPoint slide. Okay, here it is. So we have seen how to very easily generate the state machine using a state diagram, direct entry of state diagram. Okay, so these are the usual code declarations, then the reset condition, states, state conditions, transitions if required. Okay, this was what we have seen generated code already. This was the functional simulation. This was, unfortunately, I don't have a synthesizer with me, so you'll not see anything like that. Okay, the last point as far as the state machine is concerned is again state minimization. So many times we require to minimize the states in order to, first of all, reduce the hardware, the cost, increase in reliability, specifically by lowering the probability of the metastable conditions, and ultimately the faster operation. State minimization uses partitioning. Well, this is not really relevant directly to VHDL. The reason for that is your compiler will go for automatic state reduction. But anyways, you just have to understand one simple example here. So this may be an example of a state machine, a state diagram, and maybe there are some states which are equivalent and so can be reduced. So there is a procedure for that. You can go through this procedure. I'm not going to describe all these things because many times you must have already, there is a high probability that we have done all this in the lower classes. Okay. So there are, it's called as partitioning scheme. Okay. So you can just go through the steps one by one. It is self-explanatory here. I'm going to share the notes also with you. Ultimately, what I mean to say is that state minimization is done by the synthesizer tool automatically and an optimal one. So there is a less burden on the designer as far as the state minimization is concerned. Just to have the completeness, I have included this particular part. Otherwise, state minimization is really not required at this for as far as the FPGA development is concerned. Okay, so with that we finish completely with the state machine design, and I think you should now start with your assignments. Complete them within time, because I think your semester is going to get over in the first week of February. So before that, you should all submit your assignments. Is that point clear to all of you? Guys?
Yes, sir.
Yes, sir.
Fine. So I will stop here for today.